Hi everyone, happy to see you again. It's been a while since we have not given any webinar, and this is because we have been working hard on the new version of MonolixSuite. Our apps are evolving again, integrating on one hand improvements based on all the feedback we receive from you, our regular users, and on the other hand, whole new features based on ideas from our team to make your modeling more efficient. The version is not released yet. It is going to be released very soon, but we decided to give you already a preview of the most important features of that new version so that you know what to expect when you finally get the chance to download that package. To walk you through most of the new features, I have prepared a pretty typical PK dataset, and we will analyze it with PKanalix, Monolix, and Simulx. I have here the new version of PKanalix that I'm opening, and I will browse. So I create a new project, and I will browse a dataset that contains 3 studies. So I will just quickly tag it to show you the plots and observe the dataset. So in this dataset, we have some data for a parent drug. So we can split it by study to observe these 3 studies. You see that we have a crossover study, which I can also color by formulation. And I want to show you also the dosing times. And this way you see that this is a crossover study of individuals who received a single dose. And we have data for a reference and a test formulation. And we have 2 more studies for the test treatment only, a multi-dose parallel study and a single dose study. So what we would like to do now is use the crossover dataset to assess bioequivalence of the test formulation with the reference formulation on the European market. So this will be a good example to show you our brand new bioequivalence module in PKanalix. So you see here that we also have data for another observation ID, which is a metabolite that has been measured as well. And it has been measured in the 2 other studies, so the 2 parallel studies. And it has been measured for the test formulation. So you can see here. So this parent metabolite measurement that we have for the test and for the test treatment for the parallel studies will be a good data set to show you our brand new parent metabolite library in Monolix. So now I can also color this data by covariates. And so you see finally that for this test treatment, we have data for different races with apparently some effect of race on the dynamics. Exporting the parent metabolite population model to Simulx, we can check if this drug can be used in another region and plan a clinical trial with a dose that would be adjusted to the potential effects of race on the PK. So we'll use this example in the end of this webinar as an opportunity to show you all the new capabilities of Simulx. But first, let's come back to our crossover data set. So this data set I showed you at the beginning, and we will filter it to focus only now on our bioequivalence study in PKanalix. So I go here in the data tab, we still have filters available, which enable to select only the crossover study. And now that I have this filter data, I see that I don't have much information on age, weight. So age and weight are not available here. So I will just ignore these covariate columns. And I can also ignore the observation ID for this first study because I only have data for the parent, and race is also not relevant. So let me now mention the first important new feature of this version. Note that the data set that I have loaded here has now a fingerprint, which means that if any change happens to the original file here, so this text file that I have on my desktop, our apps will detect it at reload, even if the file name and the header's name do not change. So this ensures that the results are always consistent with the dataset. Now you see in the plots, I only have the crossover study that we can see a bit better if I split it by formulation sequence, and can also color it by occasion. So here you see the detailed 2 periods, 2 treatments, and 2 sequenced crossover data, and occasion corresponds to the period. So some individuals received first the reference and then the test treatments, and some received the opposite. So let me quickly show you something new here. Note that in my stratify panel, after my splits, subplots appear and I can reorder them. So I can change the order of these plots as I want. You see, if I split only by formulation, I have only 2 subplots, and I can also rename them. For example, this one, I want it to be clearly named reference, the other one, test. And you see now that it updates the title. So this is quite convenient to have plots exactly as you want to have them. So now I want to compare visually these 2 plots. So I can first set the log scale on the y-axis to see a bit better the elimination phase. And now, do you notice something new on this display panel? Now I can decide which type of mean and error bar I want to have on the plot, arithmetic or geometric, and standard deviation or standard error. All right, so I have a nice crossover data set, which makes me want to check if the 2 formulations here are equivalent. So if the test and reference formulations are equivalent. So this is one of the biggest new features in PKanalix. A complete new task that appears here in the NCA tab with this bioequivalence button. PKanalix detected on his own that we have a crossover design, as you can see here in this bioequivalence design part. Period, formulation, and sequences have been detected from the header names, and reference has been selected here as the reference formulation. I can always decide to adjust this design as I want. Note that only fixed effects are supported for now. Above here, in this parameters to compute box, you see that, as usual, I can select which parameters are computed for the NCA. But in addition, I have some parameters that have been selected for the bioequivalence analysis. So I can select the ones I want to have. And by default, we are going to look at the Cmax, the AUC until the last concentration, and AUC extrapolated to infinity. And you can also choose which ones have to be log transformed. Okay, so I can still define my usual NCA settings, such as selecting parameters relevant to an extravascular administration, a linear up, log down integral methods, and I can also decide to have a partial AUC time from 0 to 24 hours. And now I select the 2 tasks, NCA and bioequivalence, and I click on Run. And PKanalix now is running both NCA and bioequivalence analysis in a row. And I get immediately to the result, which is the most relevant to me, that is this table giving me the least square means for the different parameters in the test and ref formulations, their ratio, and the confidence interval on this ratio. So if the 90% confidence interval falls within the BE limits, which are between 80 and 125, then the formulations are considered bioequivalent. So this is when they're bioequivalent, you have this tick, green tick here. And the confidence level and the bioequivalence limits can be set in the settings. So you have also more result tables, which give you some statistics relative to the ANOVA tests performed to check impact of other factors. And you have also a table looking at the coefficients of variation. And this way you can see if it is needed to manually widen the BE limits to perform some reference scale bioequivalence. But more importantly, as for every task in our apps, we provide relevant diagnostic plots in this plots tab. The confidence intervals plot is the one summarizing the bioequivalence check. So if the interval is between the two thresholds, then it appears in green because there is indeed bioequivalence. And the sequence by period plot is a very compact way to compare the statistics of bioequivalence parameters for the two periods and for the test and ref formulations. And subject by formulation here is a plot that displays these parameters for each individual for the two formulations. So here, every line corresponds to an individual. So now, since we are in the plots tab, let me also show you a new plot that we have here for the NCA task, the individual fits. So remember, to compute NCA parameters, we need to compute the terminal slope. And this is something we usually set in the check lambda z tab, which is located next to the NCA task here. Here in the plots tab, we output all the data per ID occasion with the lambda z regression and showing which points have been used to perform this regression. So it's very nice to have it as an output plot because you can customize it as any other output plot for your reports. And actually, these points used for lambda z regression are now also outputted as a file in the result folder that you can access from here. So you see here now I have a file called points included from lambda z. And here I have a tag for each data point, which tells me if it has been included for the lambda z calculation. So that was not the case yet in the previous version. So this individual fits plot is fully customizable. And I can, for example, add the lambda z information on the plot. So to see what was the adjusted R-square, for example. And I can also use it to show observed data. So with only one plot per individual. So if I do not split by occasion like this, I can see one plot corresponds to one individual and have the two periods on the same plot. And I can also decide to color all the dots if I want, or even remove the lambda z regression. And this way, I have really raw data per ID in my report. So I can still color by occasion to have an idea of which dot corresponds to which period. So talking about reporting, to help automate the process of generating a report, including all these plots, so this new plot and also all the other plots, we have added a lot of new R functions in the Lixsoft connectors to get plots from your project and generate plot objects in R. And I will show you here a short script that we have in R. So let me just make this clean before I show you. So this script is including, so here I'm simply loading the libraries to use the Lixsoft connectors. I will do it live so you see directly how it works. And here, what I'm doing is simply loading the project. And here, using a function called plot observed data. This function will generate the same plot for observed data as I had in the interface. I run it now. And you see, now the plot that appears is exactly the same observed data plot that we have in the interface. So for each of the functions that we provide, we have the same settings and stratify options as in the interface. So if I run now this second section using some settings and stratify options, so you see the plot will appear soon. So now you see that I can split the data by formulation and color it by ID. And now note that this is a ggplot object, and this is really interesting because you can fully customize it with the ggplot R package. So for example, if I want to add a horizontal line here that would show the IC50 of my observed data, I can simply add these two lines to my ggplot object in my script. And let me run now this section. You see that I have this a custom horizontal line appearing on my plot. Also, even now within the settings that we provide in the functions like plot observed data, you see that we have more flexibility than in the interface. So here, for example, I've used a little bit more the settings. And if I run now this section of the script, I am able to plot the trend lines for the two groups on the same plot, which is something that is not available yet in the plots tab of PKanalix. So you also have more flexibility than in the interface. We provide one function per plot available in the interface. So for the new individual fits plot that I showed, we also have a connector. And here you see that I can generate the same plot showing the lambda z regressions as we had just before in the interface. So it's been generated now, but as it's a big plot, I need to zoom on it. And each time I generate it in linear and in log scale because it's always useful to be able to look at the two cases. So here you have the lambda z regressions. So you see it's very similar to what I showed you just before. And to automate this report generating process, so what you can do is get all these plot objects generated in R and input them to a small example script that I have here that is using a third-party package called Office R. And this takes as an input a Word template. So that I have here. I can show you quickly how this template looks like. So the template. This is just an example that I've been doing, but you can do any template that you want for your report. So here you can, this is a template where you decide which are going to be the figures of your report, and then you use some keywords that are going to be replaced by the plots that you will generate in R. So these are placeholders, and you will see now in the script where they appear. So you see here, these are the same names that were in my report. And what the package is going to do is going to take all the ggplot objects and replace the placeholders in the document. And now if I run this section, I'm doing it right now. And the goal is to generate this new document, which is going to be the report with all the plots. So you see now, if I go, I just generated this new document that I'm going to put here. And you see now that I have all the plots that I generated right now in R. So for example, observed data with the trend lines in linear and log scale, split by formulation and ID, colored by ID, and then you have here the different individuals. So all these plots are going to be generated in your report. So this is very convenient to automate the process, because then you just need to change the name of the PKanalix project here, and you can really generate such a report again only by running the script once. Okay, so I have shown you now how to integrate plots in the report. It is also possible to include tables if needed, getting the result tables also with our connectors. And we have here another example routine doing it. And I will show you now how a full report could look like by using such a routine. So you see that you could have really directly get from your PKanalix project the result tables for the PK parameters as a summary, the individual PK parameters with the ratio between the two formulations, and the bioequivalence analysis, exactly as I showed you in the interface, with the ratio and the confidence intervals. So this is something you can also do to combine tables and plots. So it's exactly working the same way. You have a placeholder for the table and you generate the table in R. So now let's come back to our example. We have shown bioequivalence of NCA parameters between the reference and test formulation. So now we would like to fit the individual data with a compartmental model, because you see here that it really looks like I have two slopes in the elimination phase. So it really makes me want to have a model with two compartments. So for this, we have the compartmental analysis task, which is as usual. So I can select a model from our PK library. And here I will select a model with two compartments because I have seen two slopes. I need to select good initial values before computing this analysis. So to find good initial values, as usual, I look at the data in log scale and set. So I have this auto init button as I had in the previous version, which enables me to quickly find good initial values and run. So I'm going a bit quickly here because this is the same as we had in the previous version. But do you notice here something new in this summary table of parameters? So here, since the 2021 version, I have now this whole stratification panel on the right, which enables to filter and split my table by any covariate in the dataset. For example, I can split the table by formulation, by sequence, and all the data gets updated. This stratification is also possible for the summary table of NCA parameters. And it's quite convenient to be able to calculate in a single click the statistics for each formulation and each sequence. So as I have shown you so many things in such a short time, let me summarize quickly the new features of PKanalix in 2021. The first main evolution is the whole new bioequivalence module with its settings, result tables, plots, as for any other task of our applications. The second big evolution is a list of connectors to generate plots in R and easier reporting. And I have also shown you some of the many smaller evolutions, among which we have the plot with lambda Z regressions, more options for min and SD in the trend lines, the stratification of summary tables, the dataset fingerprints, and the reordering of subplots. So now I guess you're becoming curious about the new features in Monolix and in Simulx, and we will discover them together, keeping the same example. So now I will simply export my project to Monolix. And now, as we want to focus on the parent metabolite data for the test formulation only, I will filter the data set in Monolix to keep only the parallel studies. So I can do it here in the filters. Here I keep only the parallel studies, and I will tag it again to include this time the parent and the metabolite observation IDs. I also want to keep this time age, weight, and race, and I don't need the formulation and sequence columns anymore. Okay, I also actually do not need this occasion column anymore because I have only a single formulation, a single period. So now if you have a look at the data, you see that I have a quite dense data set for parents here and for metabolite. So I'm going to look only at the single dose study. And let me set a log scale on the y-axis. Or actually, I can do the same thing for the parents. So I look at the single dose study. And this single dose study shows that the parent model needs two compartments, as we have already seen during the compartmental analysis. And the metabolite seems to follow similar dynamics as the parent. So with this in mind, we can now select a model in our new parent metabolite library, which is located here. So I can load the model from the library now, and instead of the current PK model that has been imported from PKanalix, I will now move to the parent metabolite library. So here these filters are similar as those of PK models. So I can already select the same that I had before for the parent. So oral, no delay, first order absorption, two compartments, and linear elimination for the parent. Now in this library, I can also select a distribution and an elimination for the metabolite. And as we have seen that we have similar dynamics as the parent, a simple one compartment and linear elimination should be okay. We know in this case that there is only a transformation from the parent to the metabolite. So I can select here a unidirectional transformation. If there was a backward reaction, I could have selected bidirectional. And finally, we have an option here to include the first pass effect, which means that a fraction of the parent could be transformed into the metabolite before reaching the systemic circulation. So in practice, in the model, this means that the drug can also arrive directly in the metabolite compartment. This can be known from the literature or seen in the dynamics of the metabolite, but in this case, we are going to keep a simple model without any first pass effect. And now you see, as all the models from other libraries, once you have selected all the filters, you have a parameterization with the clearance and another one with an elimination rate. Let's choose the one with the clearance. So now, as usual, after selecting a good model, we need to select good initial parameter values. And for this, we have a great improvement in the 2021 version, which is going to make your life really easier. We have this auto init button here that is doing the initialization for you, as we had before for models for the PK library only. So now this button is available for any model from all libraries and also for custom models. And you have the possibility to make this algorithm focus on specific individuals, to keep it fast, and to focus on some individuals showing specific features of the model more than others. So for example, here, I can decide to focus on the last individuals because they have a simple single dose data. And if I set a log scale here on the y-axis, you see that they contain very well the information of the second compartment. So I can select individuals 93 to 100 with the slider. You see I have the range from 93 to 100. And now I click run. And you see that I obtain good initial values very quickly for the parent and for the metabolite data. I can check that the fit is also a good starting point for the rest of the individuals. So if that would not be the case, I could expand a bit the selection here. So I just quickly save my project before I run it, as this is a good practice. And now I run the population parameter estimation with these good initial values. So even though I'm now sharing the screen, you see that the run is relatively fast. And this is because for most models of the parent-metabolite library, we have included analytical solutions, which makes the computation of these models much faster than if we had to solve the ODE system. So this is the documentation of the parent-metabolite library. And we show the runtime for some typical models here at the bottom. So here, this is the runtime for a typical data set, a typical, and then different models. And you have the runtime in case of analytical solution and in case of ODE, and we have the speed up ratio. And you see that we have a speed up ratio between twice and 5 times faster with analytical solution, depending on the model. Note that we have also included new analytical solutions for models from the PK library in case of inter-occasion variability. So now let's look at this first fit of the parent-metabolite model. We have here the visual predictive check for all the parent data, which you remember contains a multi-dose study. Oh, sorry, I want to split by study. It contains a multi-dose study and a single dose study. So to display both VPCs on the same plot as the homogeneous response to a single dose event, it is convenient to display all observations as a function of the time after last dose. And this is a new option that we have now that is available for visual predictive checks. So here in the settings, you go to display, and you can check time after last dose. And now I can put everything on the same plot, and you see that I really have a homogeneous response as if it was only single dose data. So we see clearly in this VPC that the absorption phase is not well captured, and for the metabolites, we see the same thing. In particular, there seems to be 2 different absorption phases. We should be able to capture this with one of the models of our double absorption library. But as this library is not including the metabolite, we are going to create a custom model that combines the double absorption with the current parent-metabolite model. For this, we have a new model editor directly integrated in the structural model tab here. So I can click on Edit Model, and I can remove this line corresponding to the single absorption. And to take inspiration from the models from the double absorption library, I can open also the new Monolix editor, for which we still have a separate app. And I can open an example there. So I will select the library for double absorption. And so let me keep this on the left. So here I can select a first order absorption for the 2 phases and a delay for the second absorption, given what I have seen in the data. And the rest does not really matter because I'm going to look only at the absorption part, which are these 2 lines that I'm interested in here. So I can copy these 2 lines. I can copy them to the absorption part of my model here, where I removed the line corresponding to the single absorption. And now I need to adjust the list of parameters because I have now KA1 and KA2 instead of KA. So I add these two parameters. And I also have the TLAG2, which is the delay for the second absorption, and F1, which is the fraction between leading the dose to the first or the second absorption. Okay, so you see that I can now check directly here if, so in this integrated editor, I can check that the syntax is correct. So when I click, okay, here no syntax errors were detected. And I can also directly save and apply the model here, which in this case, it encourages me to save the model under a new name because I was using a model from the library, and we try not to overwrite models from the library. So I will save it somewhere else. So if that was not a model from the library, you could just replace the file directly. So now that the new model is applied, I will find good values again to capture the double absorption. And you see again that the automated initialization is available via this button, even though I am now using a fully custom model. So I can focus on the absorption phase by looking at early times. And instead of selecting just some individuals as last time, I can also run the auto init on all of them. So either you select all of them like this, or you can just cross. And now when I run, you see it takes a bit more time to run. And this is why the option to select some individuals it can be very convenient in case of a very big data set. So here the values look good. I can, let's see if I still see the elimination. So you see I still have the elimination that looks good, and I fit the double absorption. So it's all perfect. So I'm going to use these values as initial values. And now I can run again the scenario for this new model. So if I would click on run now, Monolix would generate new results that would overwrite the previous ones. And we notice sometimes that we forget about this and we lose previous results. So that's why in this new version, we have now a warning. I click on it, I get this warning telling me that I should make sure I do want to overwrite the results. I don't, so I'm going to save my project under a new name. So parent-metabolite double absorption model. And now when I run, I don't have the warning anymore. And the run will take a bit longer now because there is no analytical solution for this custom model this time. So I'm not going to wait for it now. I'm going to open a project which has already run. So let me open directly a project that has some results. And we're going to go directly to look at so we need to generate the plots of this project. And we will see now if the visual predictive check looks better for the absorption. So it takes it. So now the VPC looks good. And talking about VPC, another improvement we have for visual predictive checks is that in this version now, in case of time to event data, the VPC will always be displayed, even if some simulations lead to not a number. So you see, it looks like we have a good structural model. The other VPC for the metabolite also looks good. But now, even if the VPC looks already good, looking at the results of the statistical tests, you see that we still need to work on the statistical model. So in particular, to include some possible effects of race on the parameters and predict how the drug would be tolerated in another population. The proposal is a suggestion of the statistical model based on the result of those tests. to find in a single click which covariate model works best, we can use one of the model building methods. And in this new version, we have a new very fast covariate search method called Samba, which iteratively applies the proposal for the covariate effects and runs the estimation of the new model until no change is suggested by the proposal anymore. So as for all model building methods, you can use custom settings. So you can decide which covariates to involve. You can lock in and out some relationships. And in this case, I have loaded a project where actually COSAC has already run. And you see that these settings that have been used have been reloaded. So this is not something we had before. Now it's the case that for all model building methods, we reload the exact settings that were used in each run so that you can really double check what you have done. So here in the results, you see that COSAC needed 6 iterations to find the best model. And now I will open a project where Samba has run to show you how it found the same results. So I did exactly the same thing for Samba. Here, same thing. In the model building, I have results, and here I have exactly the same model that was found, but in 3 iterations this time. So it was twice faster for Samba to find the same model because Samba is able to add different covariate effects at the time, whereas COSAC needs to add them one by one. So the more possible covariate relationships, the faster Samba will be compared to COSAC, which itself is much faster already than the typical SCM. And to check how much the likelihood improved with the covariate search, I have created a Sycamore project to see how the BIC decreased and to keep track of my changes. So I have this project here, and I don't know if you notice now, but the load of the Sycamore project is much faster than in the previous version. This is also an effort that we decided to put in because we realized that the relatively slow load in Sycamore could be an issue, in particular for some of your very big projects. Now it's not a problem anymore at all. So here you see I have a branch for my COSAC project and the ones where I tried Samba. And I checked also how the BIC decreased. And you see that after running this covariate search, I needed to include a correlation in my model. So this is my final project, which is the best, which includes a correlation. So I'm going to open it. And now you will notice something new with the correlations in this version. So you see the project, in this project here, I have a correlation between parameters for elimination and the rate of transfer from parent to metabolite. And now that I've included the correlation between these 2 parameters, the correlation also appears in the initial estimates tab. And this is something new that we can choose an initial value for this correlation, and we can also fix it if needed. For example, to keep PK parameters, including correlations, completely fixed when estimating PD parameters. So let me close a bit all these apps. Oh, I closed a bit too much, sorry. I need to open this last project again. So let me summarize quickly these new features that I have shown you for Monolix. I've shown you the 5 biggest evolutions. The new model editor integrated in the structural model tab, the auto init available for any model, the new library of parent-metabolite models, the new analytical solutions speeding up the calculations, and the new model building strategy, Samba. Of course, I do not have time to show you today all the smaller improvements that we included, but among them, you saw the VPC with time after last dose and the possibility to fix the value of correlation parameters, faster load of run in Sycomore, and you will enjoy more surprises when you get to use the new version yourself with your own data. So now to show you some new features in Simulx. So I will reopen this last best project again. And we will imagine now that the metabolite is the one having an effect on the PD. And we're going to simulate now a parallel trial comparing the PK for the metabolite for Asian and Caucasian populations. So for this, I'm going to export this last project to Simulx to use our favorite app for clinical trial simulation. And in this last Monolix project, we have captured the effect of race on the PK of the metabolite. So we should be able now to simulate new populations. So now in Simulx, the first feature that I really want to show you that some of you have been really waiting for is in this exploration tab, I have now an additional data panel to overlay some data on the predictions. So by default, data from the original Monolix project is selected, and I have a stratify panel here, as I usually have for plots. And I can select in the settings how to match the observation IDs to the model outputs. So you see when I map this as I want, then the data appears on the plot. And here, by default, we simulate a typical individual with this default element MlxPop in div, but I can also decide to have instead the simulation of the individual parameters. And in this case, I can link the parameters. So I can link the individuals to the IDs in the data, and I can browse to the individuals to see how the individual predictions fit the individual data. And now with this data and current fit in mind, I can explore new parameters by using these funny sliders we have now, which work very well. And we can still explore also new treatments. For example, here I can remove all these doses and create also an element from here. So I'm going to create a treatment. It's a single dose like this. Okay, and what's interesting also is if you want to display another data set to see how the current model would behave for to predict new data, you could also here unload this file and browse a new data file. So any data that you have. So now let's simulate this parallel trial. I will create a covariate element for the Asian population using this covariate distribution, which is extrapolated from the original data. And you see in this new version that this distribution is set as log normal. Since there are only positive values for age and only positive values for weight, it makes more sense to have a log normal distribution. So automatically, we extrapolate these distributions as log normal. This is quite convenient in this new version. And now I'll create an element for the Asian population. And I can also create another one for the Caucasian. So I will use these elements in my simulation scenario. So I create two simulation groups. Again, Asian and Caucasian. And I use my covariate elements. I can simulate 50 individuals receiving a single dose with this element I created. And I will look at the metabolite only because we say this is the one having an effect on the PD. So we're interested in the metabolite. And I run. And now let's look directly at the plots. We see a clear difference for the two populations. So we have a a higher peak here for Caucasian than for Asian. So what we can try to do is adjust the dose a bit for the Asian case by making it depending on the covariate race and making it a bit higher in the case of the Asian population. And what we can also do is create an outcome for the Cmax to compare the values of the two peaks. So for each individual, so I will create an outcome for Cmax. I would take the maximum value per ID. While I'm doing this, you can notice that here I have more options than before. I have first value per ID and last value per ID. And this is very convenient when not all individuals receive doses at the same time. So you can use now these outcomes. Okay, with a group comparison, I can check if the mean Cmax is not too much different in the two groups. So let's say lower than 3. I take as a reference the Caucasian group. And now I will run simulation and outcomes in a row. And let me show you the plots now. Okay, it looks a bit more similar. So we have more similar dynamics now. And the result of the statistical test here also is a success. However, as our population parameters are uncertain, it could be that this result is only true for these exact estimates that I've been using here. So the population parameter values, which are, have been estimated in Monolix. When I estimate them in Monolix, I compute errors for each of these values with the standard errors task. And now one main big improvement of this Simulx version is that we have now a population parameter element located here. So this second one imported from Monolix, which you can look at it. So what this element does is it enables to sample from a multivariate distribution defined by the covariance matrix of the estimates. So you see the matrix here, and I can select now this element instead of the population parameters elements. I select this element. And I also need to use replicates because what Simulx will do is simulating here 40 different trials, each time with different population parameters. And this way we propagate the uncertainty of the model to the predictions. You see that we have a new progress bar here in Simulx. And I get, so what I get now, so now that I have simulated the replicate, sorry, I get now the result from the 40 trials. So we see that given the uncertainty on our model, we have a 90% probability of success. So now we have looked at the Cmax, which is only one possible outcome for this PK. I may also want to look at other outcomes like AUC or any other parameter from an NCA analysis of this simulation output. I may also want to check the bioequivalence of the dosing regimen for the two groups as if the trial analysis was performed by NCA. And as PKanalix is the perfect tool for this now, we have a new easy way for you to export all the simulated data as a PKanalix compatible dataset, which is actually also Monolix compatible, simply by clicking here on Export Simulated Data. And in the result folder now, I have a dataset that I can directly load in PKanalix. I will do it quickly now just to show you. So let me just copy this address. I can create a new project in PKanalix, load this data which was exported, and I have now a column. So this is all the simulated data. I have my different groups, and I have a column UID for unique ID, which is a unique identifier for each ID of each replicate, which I can use as ID. And I can decide either to use all these individuals or filter only, just need to define an observation. Or I can decide to filter only one of the replicates. So if I can again use the filters in PKanalix here, and I can focus on the first replicate by selecting here all the IDs for which replicate equal 1. And once this data is filtered, as I showed you at the beginning of this webinar, in a single, or actually maybe 2 clicks, I can run the bioequivalence analysis, which shows in this case, let's see what it shows. We have bioequivalence for Simulx, but we do not have it for AUC. We see it in the table and more visually also on the plot. And this is where we started from. So we can say the circle is complete. But before I leave you for a few weeks, longing for this new version, let me just sum up the Simulx new features. We have seen how the uncertainty of the population parameters can be propagated to the predictions with our new predefined elements based on the covariance matrix imported from Monolix. We have seen how easy it is now to export simulated data from Simulx to use it potentially in PKanalix or in Monolix for further investigations. And the overlay of data of any data set on predictions in the exploration tab is also possible now. And as in Monolix, you have not seen it here, but the model editor is also fully integrated now in the model definition tab of Simulx. And as for PKanalix and Monolix, we included many more small tricks which make the simulation more convenient for you. And I'm sure you will enjoy discovering them as you work on your own projects. Thanks a lot for attending this webinar. I hope you enjoyed and see you very soon.